This is 40 days of chemistry, 5 minutes at a time, part 1, getting us ready for the HSC exam. This is 9.4.1, the first part of chemical monitoring and management, all about monitoring and collaboration in chemistry. That's what we're doing in the speech. If you want to read it, you better pause it, because we're moving on. The first thing is, what types of chemists are they and what do they do? There are a range of chemists. There are too many to list. Here's a few examples. Analytical chemists look at what chemicals are present in a sample. Research chemists look at new chemicals or new processes. Environmental chemists usually look at pollutants in the environment. Industrial chemists look at processes such as the Haber process and how to improve them. Nuclear chemists mainly look at radioisotopes, and forensic chemists look at evidence and crime scenes. But there are many, many, many more. That's just a snapshot. The next thing we looked at was, what is collaboration? Well, collaboration is working with each other, so chemists working with each other to achieve a shared goal. And why do they collaborate? Well, there's a few reasons why. Here are 3 examples. First of all, to share expertise necessary to achieve the goal. Not all chemists are experts on all the same equipment, or have all the same analysis techniques, or have the same knowledge. So they have to come together and apply and combine their knowledge and expertise to achieve the goal. As you know, working together in teams, you generate new ideas about how to achieve the goal, and also the more people working on a task, it increases the speed of the task. Now, as we know, in 2012, they asked a collaboration question on batteries, which was quite weird, but that means they could use any example they like now to ask questions about collaboration. So, for example, you might be asked a question about, on the Haber process, why might chemists need to collaborate? Well, drawing on a few of those examples we used before, you might have industrial chemists working in the plant itself, trying to optimize output. You might have research chemists researching new catalysts. You might have analytical chemists looking at the product, or looking at the product or the input gas streams to try and purify them. You might have environmental chemists working together to make sure there's no pollutants. So as long as you know a range of chemists, you should be able to talk about why they collaborate on any given task you're provided with. The next thing we looked at was some practicing Australian chemists, and the first was our male chemist. Many people looked at Dr. Stevens Brumley. He was a biochemist working at University of Queensland, but unfortunately he's just moved to Texas University, which is not in Australia. I don't think it's going to matter that much, but if you're really worried about it, one of his colleagues at University of Queensland called Peter Halley is also a biochemist, and he has developed an Australian biopolymer called Plantic. It's actually made of cornstarch. It's quite fascinating. It's very current. He uses the principles of polymerization as well, so you want to look at him, you're more than welcome to look him up instead. But Stevens Brumley, he was developing GM sugarcane to manufacture PHB. We know it's a renewable biopolymer because petrochemicals are running out. The chemical principles you can associate with his work is, first of all, catalysts, because the enzymes that produce PHB are a form of biological catalyst, but also just condensation polymerization itself is a principle used in the manufacture of PHB. Moving along to the practicing female chemists, there were a range that were chosen. Many chose Suzanne Smith, who works at Ansdale as a nuclear chemist. She made copper-64 for diagnosis, and the principle there was radio tracing the path of a chemical by the radiation it emits, particularly if it's an isotope, obviously. Then you had Professor Maria at University of New South Wales, who's an electrochemist. She developed the vanadium battery, and her principle is redox, specifically galvanic cells. If you separate the oxidant and reductant, you'll produce a current. One other one I've used in the past, which may be relevant now we've studied steels for shipwrecks and corrosion and conservation, is Veena Sahajwala from University of New South Wales. She's a metallurgist. She developed green steel by using waste plastic rather than fossil fuel coke, which is a form of a coal, in steel making. Her principle is redox, because the carbon used from the coke or the plastic is used to reduce the iron oxide back to iron again in steel making. Next, why do reactions have to be monitored? We studied a whole of this throughout the whole of chemical monitoring management. The first one we're going to look at today in detail is why some reactions have to be monitored, because they produce different products in different conditions, and they're monitored to ensure safety, efficiency, profit output, and minimize pollution. In the Haber process, we looked at how you have to monitor reactions for yield and rate, and in particular you're relating yield to Le Chatelier's principle, so anything that affects yield, which is percentage conversion of reactions to products, and is also related to Le Chatelier's principle. So things like temperature, things like pressure, things like concentration, they can all affect the yield, and they've got to be monitored. Things that can affect rate of reaction are also very important. Sometimes you want to speed reactions up, such as Haber process. Sometimes you want to slow them down, like corrosion. So you've got to monitor, once again, temperature, pressure, concentration, but also catalysts too can affect your rate of reaction. As we studied in the CFC topic and also the AAS topic, some things produce pollution, and those pollutants have to be monitored to make sure they're not damaging the environment. With AAS we study lead, for example, at Port Pirie. And finally, sometimes monitoring can be diagnostic. We monitor water, for example, before it's treated, so we know how to treat it. But our big case study in this topic was combustion monitoring. We know that hydrocarbons such as octane are the main source of energy in transportation, and those hydrocarbons are combusted, producing energy, but also water and carbon dioxide if it's complete combustion. But to achieve that, you've got to have this ideal or stoichiometric ratio of fuel to air. And to achieve that, you've got to monitor the fuel to air ratio, and that's done by using oxygen sensors actually in the exhaust system of the car. And they're connected to a feedback loop to the engine, to the fuel injection system, to try and maintain that correct fuel to air ratio. As we said, if you get the stoichiometric fuel to air ratio, it's good. You get complete combustion, which means you get maximum energy, and you only get carbon dioxide and water in your exhaust. We know carbon dioxide is a pollutant, but it's not as bad a pollutant as the other ones you can possibly produce. For example, if you've got a rich mixture, which means you've got rich fuel or excess fuel and not enough air, that means you don't have enough oxygen for complete combustion. You get low energy output, which is bad. You also produce carbon monoxide, which you know is a deadly poison, carbon soot, which is can clog engines, but also it's a particle pollutant, and also unburned hydrocarbons, which sometimes are called VOCs, volatile organic compounds, and they contribute to pollution as well. If you've got a lean mixture though, which means you've got low fuel and too much air, what you can get is that excess air or excess oxygen in the engine can actually react with nitrogen in the air to produce nitrogen oxides, and we know that nitrogen oxides lead to acid rain and smog, which is the same thing as ground level ozone, which are bad sorts of pollution. So you want to make sure you've got this correct air to fuel ratio, which means it needs to be monitored. Now there are things in your exhaust, just as an aside, called catalytic converters, and they can reduce nitrogen oxides back to nitrogen, and they can help to completely combust these incompletely combusted hydrocarbons, but they're not perfect, and if you've got too much of these pollutants in the exhaust stream, they won't work. And that's it. That's 9.4.1, hopefully in about 5 minutes.